Okay. Yes, this does look, whatever it was that you just said, terrible, bad. The most difficult part is just memorizing all the steps. If we're going to find the domain of this function here, these are rational functions, by the way. The way that you find the domain of a rational function is you take whatever is on the bottom of the fraction, set it equal to 0, and solve. That's not hard. It's just remembering that's how you find the domain. That's the hard part. Now, here's what this means. X cannot be -2. How do we write that in interval notation, you may be asking? Well, like this. -infinity to -2 union -2 to infinity. So that's how you're going to find the domain of a rational function. Set the denominator equal to 0 and solve. That tells you what X cannot be. Holes, also another thing that's really not that difficult. Maybe it requires more steps than domain, but it's just remembering how to do it. That's the difficult part. Here's what you're going to have to do. You have to make sure your function is fully factored first. This one's not. I'm going to factor it quickly. The top portion of that fraction simplifies to that over x plus 2. Fully factored. Now you want to see, do we have any factors that cancel one another out? And we do. Leaving us with only y equals x plus 1. That's our new function. In order to determine where does the hole occur in this graph, you're going to take one of the factors that canceled, set it equal to 0, and solve. If we did that, we'd get -2. Now, that's not our final answer. That's the x value of our final answer. We now take that -2, substitute it back into the function once we simplified to figure out what the y value is at that point. So we're going to have a hole in this graph at -2, -1. And if we have to actually plot and graph holes, I'll show you how to do it. But for this one, we don't have to do that. We just have to identify where it occurs. Roots. Here's what you do. You take the top portion of the fraction, you set it equal to 0 and solve. X squared plus 3x plus 2. This can be factored. So let's factor it. In fact, it's the exact same factors as the previous problem. So make sure the top portion is fully factored. If you set each of these equal to 0 and solve, we'd get -2, we would get -1. Those are our roots. Those are the x-intercepts. -2, 0, -1, 0. Hopefully you see what I mean when I say somebody drew that. How sweet. Hopefully you see what I mean when I'm saying that it's not difficult. It's not difficult math we're doing, but you just have to remember all this stuff. Asymptotes. We're about to solve for our vertical asymptotes here. And the way that you do that, in a way we've already done it. You set the denominator equal to 0 and solve. Set the denominator equal to 0 and solve. X equals -2. That's our answer. We're going to have a vertical asymptote at x equals -2. And later on, I'll show you how we actually graph that. Tangency and togetherness. Just read over that in your own time. Commit it to memory if you want. I'm actually going to show you in just a second what that would look like on an actual graph that we'd have to work out ourselves. Okay. Going on to this next section here, we have in-behavior asymptotes, also known as horizontal, maybe oblique asymptotes. So you're going to hear me say, whenever we're trying to figure out what our horizontal asymptote is it top heavy, bottom heavy, or evenly distributed? And here's what I mean by that. This very first example is an example of bottom heavy. The way that you identify that is you highlight the x terms that have the highest exponent. Highlight the exponents, the x term on top of the fraction and on bottom of the fraction, and then compare the exponents. This top one has an exponent of 1. The bottom one has an exponent of 2. Well, since 2 is bigger than 1, and 2, the square, is located on the bottom of this fraction, this is bottom heavy. If your rational function is bottom heavy, that means your horizontal asymptote is y equals 0 every time. I like bottom heavy ones because it's, you don't have to do any math. It's bottom heavy, y equals 0. I'm going to skip this one for now. We're going to come back to it. This one's the one that requires the most amount of work. This one here, if they're evenly distributed, once again, we're looking for the x value on top of the fraction and comparing it with the x value on bottom. Looks like they're both x over x. Don't worry about the coefficients right now. That's even. They're the same. If that is the case, then compare the coefficients, the numbers in front of the x values. In this case, it'd be 2 over 1. So our horizontal asymptote is y equals 2. That's how you determine horizontal asymptote if it's evenly distributed. And now the one that requires just a little bit more work. If it is top heavy, look for the variable with the biggest exponent on top of the fraction. Look for the variable with the biggest exponent on the bottom of the fraction. This is an example of top heavy. If that is the case, then you do not have a horizontal asymptote. But wait, you might have a oblique asymptote or slant asymptote. And I say might because here's how you can determine whether or not you have a slant or an oblique. If the difference in your exponents is a difference of 1, then you have an oblique asymptote. So this exponent is 2. This exponent is 1, a difference of 1. We have an oblique asymptote. How do we figure out what that is? I'm glad you asked. Let me start setting it up. Do you see where I got that information? X plus 3, the factor on bottom. I actually want to use synthetic division. We want to divide that by -3. And then this terminology that we have on top, that's what we're going to use in the other portion of our synthetic division. And remember, you can't skip variables. That's why I had to account for 0x. And we did this last unit, so let me just get through it. Bring down the 2, multiply, combine, multiply. Now, I think you're going to like this. This right here represents our remainder. Whenever we're finding a oblique or slant asymptote, we don't need that. Don't need it. You just need the stuff before it. Don't forget, your variables decrease by 1 exponent. So our oblique or slant asymptote is y equals 2x minus 6. That's the answer. Y equals 2x minus 6. Once again, the math isn't really that hard. It's just a lot of things you're going to have to remember. Y-intercept, we've been doing that for a while. We'll do some of those. Oh, before we, you see the graphs and you might be thinking, oh no, we're gonna have to graph this stuff. Well, for our notes purposes, yes. As far as how much stuff are you actually going to be having to graph on this unit, I would assume probably not much. So try not to stress a lot about these graphs here. This stuff right here, and that's the stuff you're going to want to know. So let's get to it. To find the domain, remember, you're going to restrict the domain by setting the bottom portion of this fraction equal to 0 and solving. That would give us -5. That's what x cannot be. Set the bottom equal to 0 and solve. X cannot be -5, so this is how we write that. To solve for holes, make sure that you're fully factored, which we are, and see if any factors will cancel. They won't. So none here. To find your roots or x-intercepts, take the top of the fraction, fully factored, by the way, which this is. Set it equal to 0 and solve. And that would give us 2. So we have an x-intercept of 2, 0. Asymptotes. Let's find the vertical first. Those are the easiest ones. And we've already done it. You set your bottom of the fraction equal to 0 and solve it. We already did that. So we're going to have a vertical asymptote at x equals -5. Now to find the horizontal, y equals, we want to determine top heavy, bottom heavy, or even. Those x values have the exact same exponent, so it's even. Their coefficients are 1 over 1, which simplifies to 1. So we have a horizontal asymptote at 1. Tangent or togetherness, none in this case. We're going to have an example of that in just a moment. And the end behavior asymptote is going to be the y equals. Whatever the y equals is, that's the end behavior asymptote. So y equals 1. And the way you find the y-intercept of any function is take your fully factored function, set it equal to 0. I'm sorry. Everywhere you see an x, plug in a 0, and then solve. So -2 over 5. That's our y-intercept. Now, if you have to graph this stuff in the future, here's how you're going to do it. You want to start with asymptotes. So I'm going to graph x equals -5 by going to -5 on the x-axis, 5, and then drawing a vertical line. To do the horizontal, let's go to where y is 1 on the y-axis and then draw a horizontal line going through it. Now plot any coordinates that we happen to know. We know an x-intercept, 2, 0, and a y-intercept, 0, -2/5. Don't stress about being perfect. Now, I don't want you to stress yourselves out too much over what I'm about to do. I've been doing this for a while, so now I have an idea what this graph is going to look like. It's going to look something like this and that. Don't worry too much about this. You might not have to graph once on this entire unit. You're going to have to know how to do that stuff. If I feel like we're going to need to actually graph this stuff and have a fair level of comprehension, I will make sure and cover that on review day. Yes. Is that a question? And no, not a question. All right, example 2. Domain. The way you find domain is you set the bottom equal to 0 and solve. In this case, that would say x cannot be -5. Holes. Well, you would want to make sure this is fully factored, and it is and it isn't. Okay, nothing's going to cancel, so none once again. The roots, take the top portion, set it equal to 0 and solve. So we have an x-intercept at 2, 0. Asymptotes. We've already solved one of them. Remember when we restricted the domain here? We got x cannot equal -5. So that means one of our vertical asymptotes is x equals, -5. Now for the horizontal asymptote, top heavy, bottom heavy, or even, it helps when these are in standard form, but this one's not. If you multiply these two factors, x times x is x squared, meaning we would eventually have x over x squared. This is bottom heavy, so y equals 0. Now, tangency or togetherness. This one has togetherness. How can you tell? And by the way, it's at -5. The way that you can tell, how do we know if we have togetherness or tangency, is you're looking for a parenthesis that's being squared. That tells you that you're going to have togetherness or tangency. Well, which one is it? Well, since our parenthesis that's being squared is on the bottom of the fraction, that means we're going to have togetherness at -5. That's how you can tell. In behavior asymptote, remember, that's always going to be the y equals 1. And just some quick math for you here. If you were to plug in 0 into this function and then solve, you would get, for your y-intercept, -2 over 25. And now we have enough information to graph. Let's do it. 1, 2, 3, 4, -5. Our horizontal asymptote is y equals 0. Let's plot any points that we know. There's our x-intercept. Here's our y-intercept. Now here's what this portion of the graph would look like, something like this. Now, since we have togetherness, we can assume that the left portion of the graph is going to look something like this. They're going to meet, they're going to start coming together at the vertical asymptote. That's what togetherness looks like. Don't worry too much about the graphing portion. And now example 3, first of all, well, it's not fully factored, so let me do that real quick. Okay, now it's fully factored. None of those factors are going to cancel, so no holes. And remember, in order to find domain, you have to take what's on the bottom, set it equal to 0, and solve. This time we have two numbers that x cannot be. X cannot be 4 or -3. So here's how you write that in interval notation. You want to just think from least to greatest. From least to greatest. Roots, in order to find x-intercepts, take the top portion of your fraction, set it equal to 0, and solve. For our vertical asymptotes, we've already done that. When we restricted the domain, we found our vertical asymptotes. To find the horizontal, we have to determine top heavy, bottom heavy, or even. This one's going to be even. Here's how you can tell. Well, we fully factored here, right? If we were to multiply this together, we'd have x times x, which is x squared, over x times x, which is x squared. I don't need to do any more math. These are going to be my leading terms. They're the same. So look at the numbers in front. The number in front of x squared is 1. 1 over 1 simplifies to 1. Tangency or togetherness. This one's going to have tangency at 2. How can you tell? Well, we're looking for a parenthesis that's being squared here. This one's being squared on top. So that's tangency or bounce. Bottom. Yep. In the behavior asymptote, remember that's the y equals. And if you were to solve for your y-intercept correctly, remember, plug in a 0 everywhere you see an x, and then simplify, you would get -1/3. Now here's how you would graph something like this. I'm going to do my vertical asymptotes first. And then the horizontal. We're going to plot any coordinates that we know. So that would be the y-intercepts and the x-intercept. Tangency means we're going to have a balance. It kind of looks like a parabola, but not necessarily so. Bounce. And because I've been doing this for quite a while, I know that the remainder of this graph is going to look something like this. Don't worry about that, though. All this stuff here is the most important stuff. Okay, please flip over to side 3. Side 3 is going to be our last portion of today. This is a really good indicator of a lot of what you're probably going to see in your next test. They're going to give you different functions and say, hey, find the domain of this one. And if you see one like this, hopefully you remember, well, the way that we find domain is you take the bottom portion of the fraction, you set it equal to 0, and then solve it. Meaning we'd have to subtract 9 from both sides. Square root both sides. So x equals plus or minus 3i. What? Are those real numbers? No, they're imaginary. So that means our domain in this example is all real numbers. Every time we did domain earlier, we had real numbers. Feel free to go back and look at your notes at how you would write your domain if we have real numbers. Okay, let's skip over 2, but let's take a look at 3. In order to find holes in a graph, fully factor. So that trinomial on top simplifies to that. On bottom, we have a difference of perfect squares. Those factors are going to cancel one another out. So our new function is that rational expression there. Now, in order to figure out, well, where in the graph does a hole occur, I'm going to go ahead and set up a set of parentheses for my coordinate. We're going to look at these set of parentheses that just canceled one another out. Set it equal to 0 and solve. That would give you -1. You now take that -1 and substitute it into the new function everywhere you see an x. To get -1/2. So this is where the hole is going to occur in the graph. We're going to skip 4 and 5. We've been solving for vertical asymptotes a few times now. Looking at example 6, find the end behavior that's top heavy, bottom heavy, or evenly distributed. This one is even. So when it's even, look at the numbers in front of the coefficients or variables. And then simplify. Y equals 2. And then the last one that we're going to do example 7, find the intercepts. Let's start with the x-intercept first. So take the top portion, set it equal to 0 and solve. You could factor here. It's one way. Now, you would set both of these equal to 0 and solve, but the only one that would give you a real solution is that factor that we have in parentheses. And your y-intercept here would be 4. Everywhere you see an X, plug in a 0 and solve. And if you did that, I guarantee you, you get 4. We have now found our intercepts. The rest of the notes, what I have skipped over, there's also a side 4 is extra practice if you feel you need it. Thank you.